Okay, now we're going to look at what happens when we make our c values even bigger than plus 2. So for example, plus 5 here, x plus 5 squared, plus 7 here, x plus 7 cubed, and then we have a plus 6 here, the absolute value of x plus 6. What happens when we add bigger numbers to our x values within a function? Again, we're looking at horizontal shifts, and we looked at in the last video, basically to compensate for these pluses, we have to ultimately subtract from our original x values to compensate for that. We looked at why that was algebraically. So let's go back to the graph. Let's look at x plus 5 squared. So we're going to make our c value plus 5. Okay, and as you can see, what happens graphically when we make c plus 5, again, we can see that the transformed graph shifted 5 units to the left from our original graph. In other words, the x values were subtracted by 5 to have the same y values as our parent graph. Again, let's look at another one. Let's look at x cubed. Let's look at this one. Again, we can see that when we make c equal to positive 5, it also shifts c to 5 units to the left from the parent graph. And again, that has to do with algebraic compensation. We have to subtract 5 in order to end up with the same y value. So the best way to remember this is whenever c is 5, positive 5, the graph will shift to the left. Okay. Let's look at, let's see, what was the other one we're going to do? Okay, absolute value of x plus 6. Okay. So when we make c plus 6, we again can see the v shifts 6 units to the left. So whenever c is plus 6, it shifts 6 to the left. Now again, I want to explain why that is, and I don't want you to just think, okay, we're just going to do the opposite. And that is a good way to think, but we want to see why that is. So suppose p of x plus c is equal to f of x. So for any positive c value, we take our parent function, we add c units to it to get our transform function. What happens? Now again, we want to find a value for x2, in other words, our transformed function's x value that will give us the same y value as our original parent function. In other words, p of x1 is equal to f of x2. Well, f of x2 is going to be the same as p of x2 plus c. That's our definition of our transform function. And in order to get the same y values, what's inside what we're plugging in must be the same. So we're going to set x1 equal to x2 plus c. Very similar proof to what we did in the last video. If x1 is equal to x2 plus c, that will ensure that our y values will be the same. So that's what we're going to do. We're going to set x1 equal to x2 plus c, subtract c from both sides, and here is the gist of it. Whenever we add c to an x value, we must subtract c in order to end up with the same y value. So in other words, our graph will always shift c units to the left. Therefore, x1 minus c is going to be equal to x2. In other words, take your original x values, subtract c from them to get the new x values for our transform function. That will ensure that we have the same y values. Let's reiterate. So when x1 minus c is equal to x2 and p of x plus c is equal to f of x, in other words, take our parent function and add c to our x values to get our transform function, what's going to happen? Well, first of all, let's replace x with x2. In other words, our new x values. Okay, by substitution, we know that x2 is equal to x1 minus c, so we're going to replace x2 with x1 minus c. And then we can see algebraically what happens. These c values will cancel, and we've proven what? We've proven that p of x1 is equal to f of x2. In other words, the original x values that we plugged in for p is going to give us some y value that's going to be the same as our new x value, x2. When we plug that in for f, we will get the same y values when we plugged in our original x value into our parent function. And again, that all happens when we take our original x values and we subtract c from them. Let's look at what that looks like on a chart. Again, here is our standard parent function. These are our usual x values, range from -2 to 2. And what we really want to do is whenever we add c to our x values, we want to compensate for that in our chart by subtracting c from our original x values. And we just get a generic -2 minus c, -1 minus c, 0 minus c, 1 minus c, 2 minus c, so on and so forth. Notice though, the whole reason we're doing that is so we can keep our same y values. Now, why do we do that? Why do we want to keep the same y values? That's because we know that for our parent graph, we can with our transform graph, we can compare it to the original parent graph without having to go, too far off the graph. So what happens a lot of times? Let's just kind of zoom into, let's say 6, and let's reset here. Or let's do something like let's do something like a cubic function here. So what happens is if we make c too big, or actually let's use an a value for right now. If we make a too big, our y value is going to get really big really quick. So you're going to see that if we don't have this method of using the original x values, the graph can go completely off of our standard zoom and we can't even compare them. Okay, so in general, our transformed function, we just take the original x values that we normally use, and if it's p of x plus c, we subtract c from those x values, and that will ensure that we maintain the same parent function values. Okay, horizontal shift. What is the definition? It's the number of horizontal units the parent graph shifts to reach the transformed graph while keeping the same y value. Again, we can see that here. Let's go back to x squared. I kind of like that one better. So if we make c equal to positive whatever, let's say positive 4, then it shifts c units to the left, so on and so forth. Okay, so when f of x equals p of x plus c, then the parent graph p of x will shift negative c units to reach the transformed graph f of x while keeping the same y value. Therefore, the horizontal shift will be minus c, and p of x will move negative c units to the left to reach f of x. Alright, that's it for our horizontal shift. Whenever c is positive, the graph will actually move c units to the left. If you have any other questions about this lesson, let me know.